Hello once again, this is Mr. Wakefield doing section 3.4 here in Math 130. Looking at, let me zoom in here for you. But we're going to be looking at graphing polynomial functions, all right? Now we have graphed some polynomial functions before, but this method here looks at some of the bigger ones in particular and how to do those ones. We saw some earlier where it was f of x equal to a polynomial that where the highest degree was x to the second, all right, and it ended up being a parabola and all that. But what happens when the highest degree is bigger than that, such as here it's 3, and then we'll see some other ones even bigger than that as well. Starting out here, what you would do in that situation where the degree of the polynomial that f of x is equal to is bigger than 2, all right, in this case 3, is we first of all start out with graphing the x-intercepts, and also it says graph the y-intercept. All right, now we know that when you graph the x-intercepts, that means to set the y equal to 0. Okay, so x-intercepts means that the y is 0, set y equal to 0, and then y-intercept means you set x equal to 0. All right, we'll get to that. Now, setting y equal to 0 is the same thing as setting f of x equal to 0 because y and f of x are the same. So it's starting to sound like what we did in the last section, not a coincidence, all right? So I'm going to set the f of x equal to 0, and let me go and write that out. So when you set the function equal to 0 like that, and you want to solve that equation, when the degree of the equation, meaning what's the highest degree term, if it's bigger than 2, that means it's neither linear nor quadratic. Okay, this is degree 3. So we need to go through that process when the highest degree of the equation, with a polynomial on both sides, that is. But if you got a polynomial on both sides, but this time, unlike linear and quadratic, where the highest degree is bigger than 2, then you want to go through this process that we saw in the previous section where you, after you set the f of x equal to 0, we already did that, you factor out the GCF if there is one, and there isn't one here. It's not equal to 1, in other words, so you can skip that step. The next thing we do, though, is if after you do the GCF step, if what you have left over is still degree 3 or higher, which it is, it's degree 3, we use synthetic division to try to factor it into 2 factors. But like we saw near the end of the last section, if the problem doesn't already give you a 0 to try, and it didn't give me any clues here, we first of all try to do the conjugate zeros theorem, but we can't do that here because there's no imaginary numbers to try here. And to be honest, you guys, when you're looking at graphs of polynomial functions, there's no imaginary numbers on there anyway, and so we don't want to be dealing with that anyhow. When we're talking about graphing, you can't graph an imaginary number. So we can't do the conjugate zeros theorem, so we then have to fall back on this last option here. Like we said in the last section, the last option is the rational zeros theorem. Let's go ahead and take a look at that once again. With the rational zeros theorem, you take the coefficient of the term that doesn't have the variable in it. Let's write this down here at the bottom because we're going to need room, so please put this at the bottom, all right? Factors of 10 is what we're going to look at in the numerator, and then in the denominator we're going to look at factors of the highest degree term's coefficient here, the leading coefficient of the highest degree term, and of course that's 6. And so what are the different combinations of possible factors when the top is factors of 10 and the bottom is factors of 6? For factors of 10, we've got plus or minus 1, plus or minus 10, plus or minus 2, and plus or minus 5. Underneath that, we've got plus or minus 1 and plus or minus 6, plus or minus 2, and plus or minus 3. All right. So taking all the different possible combinations of that, that's actually a lot of stuff right there. All right. Doesn't mean we're going to have to test it all. All right. But 1 over 1 is 1. 2 over 1 is 2. And we look at all the different combinations. 5 over 1 is 5. 10 over 1 is 10. And then we try out the 2 down here on the bottom. We go 1/2, 2 over 2, 5 over 2, 10 over 2. Let me write that down. So I got plus or minus 1/2. Plus or minus 2 over 2 is the same thing as plus or minus 1, so you don't have to write it again. Plus or minus 5 halves. Plus or minus 10 halves, but that's the same thing as this one right here, plus or minus 5, so you don't have to write that again. We then look at the 3. We got 1/3, 2/3, 5/3, 10/3. Plus or minus 1/3, plus or minus 2/3, plus or minus 5/3, all right, and plus or minus 10/3. All right. And then for the 6, all right, we've got plus or minus 1/6. You're usually not going to have to do the fractions here, but this is good practice anyway here. 1/6, 2/6, 5/6, and 10/6. All right. We've already got 2/6 because it's the same as 1/3. 5/6, I don't have that one yet. And then finally, 10/6 is the same thing as 5/3. So even though we usually don't need to worry about the fractions, all right, as far as breaking down the problem to where we need it to go, which is linear and quadratic factors, in order to find the zeros. By the way, that is what we're doing here. We need to find the zeros, you guys, because the zeros are the x-intercepts. All right, remember, zeros are numbers that when you plug them in, they make the function or the y value, same thing, equal to 0. And that's what an x-intercept does as well. All right. So zeros, as far as the graph is concerned, is the same thing as an x-intercept. So we want to find the zeros here. You just need to break this thing down to linear and quadratic factors like we did in the last section. And as I promised you, okay, you should be able to use one of the whole numbers here to be able to at least get it far enough to where you can get it into linear and quadratic factors. Again, to save time here, one number that works here would be 2 in the synthetic division. So you put the non-zero side of the equation, just like we did in the last section. You put that inside the bar here. And we need to factor that. That means we need a remainder of 0. I can tell you right now that 2 is going to work just because I've done the problem before. All right. 29 times 2 is 58. Negative 5. And then times 2. And then add again and you get the 0 that we want there. Since that's 0 right there, okay, that means what? That means that this polynomial that's on the left-hand side of the equal sign is going to break down to what? It's going to break down to x, and then you change the sign of what's outside the synthetic bar. So that's going to be x minus 2. And then we take this bottom line right here, not including the 0, and we're going to get 6x squared, plus 29x minus 5. All right, now that I've got it broken down to linear and quadratic factors, you guys, I can now set that equal to 0, set those two factors equal to 0. X minus 2 is equal to 0, or 6x squared plus 29x minus 5 equal to 0. All right. And so x minus 2 equal to 0 is going to be what? That's going to give me x equal to 2 when I move the 2 over, right? All right. But what about the other one there? The other one, I need to factor that. The Berry method tells us that we need 6 times negative 5 is negative 30. What two numbers will add up to 29 that are factors of negative 30? How about 30 and negative 1? All right, those are factors. They equal negative 30 when you multiply them. They're factors of negative 30, but they also add up to 29. So I get 6x plus 30. 6x minus 1. And then when I factor out the GCF out of each one of those, I get the first one is going to be x plus 5 if I factor out the 6. The second one stays the same because the GCF is 1. And now finally I can solve this thing here. When I set these equal to 0, I get what two answers here? I get, this first one is going to be x equal to negative 5. And the second one here is going to be x equal to, if you move the 1 over and divide out the 6, like we always do there in the linear equation, I get 1/6. Okay, so finally, after all that, I have now solved that equation where I set y equal to 0. That means that these three numbers, 2, negative 5, and 1/6, those are all your x-intercepts. That means that they go where? They go on the x-axis at x equal to 2, x equal to negative 5, and x equal to 1/6, which, as we know, is sandwiched between 0 and 1, okay? If you put that in your calculator, you'll realize that 1/6 is closer to 0 than it is to 1. But as long as you put it halfway, somewhere in between 0 and 1, I'm fine. I'm not going to be any more picky about where you put it than that. All right. So those are your intercepts as far as the x-intercepts are concerned. It also asks for the y-intercept up here, which is a lot easier to figure out. You just plug in x equal to 0. You write that down up here. Y-intercept is going to be, when you plug in 0 into f, and so that's going to be 6 times 0 cubed. And I think you can see where this is going here. We've said this before. When you plug a 0 into a polynomial, no parentheses, just a normal polynomial, bunch of regular monomial terms being added and subtracted together, the terms that had the x in it are just going to become zeros. And so you just get a bunch of terms being added and subtracted that are equal to 0, and then you got plus 10 at the end. So as you can imagine, then the answer is going to be 10 because everything else is just zeros. Don't plot that yet, though. I'm going to have to change, as you'll see here in a moment, I'm going to have to change the scaling on the y-axis. So don't plot the 10 yet. All right, changing the scale on the y-axis will affect where that point goes, but it will be at y equal to 10 no matter what, though. The next thing we got to do is we have to, and let me make a little bit more room here by moving this arrow out of the way. But we need to make a number line. We talked about this in some other problems in the past but you do it with the x-intercepts this time. Okay. And I went a little bit too far, as you're going to see here. I don't want to go that far over. You take all of your x-intercepts. Since we have 3 of them, we put them on here, but we have to put them on here in such a way, as usual, that the smallest number goes on the left, the biggest number goes on the right. So 1/6, 2, all right. And that breaks this interval up into 4 parts, doesn't it? All right, and just like we've done in the past, what you're going to do is you're going to plug in a test number inside of each interval, and you're going to plug it into the function. It's going to tell you what the answer is there for that, and that's going to affect our graph. So pick any number in between negative infinity and negative 5. Negative 6 sounds like a good choice right there. I'll plug that in. So f of negative 6. If I plug that into here, okay, just plug it in the same way you normally would. It's going to be a really big number, you guys. All right, I won't put all of the details on here. We know how to plug that in. We know how to do where you do the exponents first before the multiplication, and then the addition and subtraction last. So I won't put all those details on there. I'll let you figure that out off to the side, but it ends up being equal to negative 296. Again, you just do the normal thing where you plug in the negative 6 and then figure out what the function value is equal to right here. Plug in negative 6 right here. It ends up being negative 296. You might be thinking, how in the world am I going to plot a number that big? We'll get into that, all right? As it turns out, you're not going to have to when it's the first number here in the first interval. What's a good number to plug in for in between -5 and +1/6? Well, 0 is usually a good number to plug in, all right, as long as it's in your interval, and 0 is in that interval, okay? As a matter of fact, we already figured that out, didn't we? We already figured out that f of 0 is 10, so, hey, that saved us a little bit of time right there, all right? We didn't even need to do any more work there. It's okay to do that, though, even though we already got that point, that's fine. And then between 1/6 and 2, all right, number 1 right there, the number 1 is in between 1/6 and 2, okay, and so if I plug in 1, I end up getting, again, you just plug it into here, and it ends up being equal to -30, all right, when you do all the work on that. And then finally, between 2 and infinity, a good number to plug in would be 3. You could also plug in 4 or 5 or 6, but I'll go ahead and do 3. All right, if you plug in 3 and you do all the normal work on that with your calculator helping you out, that'll be 136. Okay, now, here's what we're going to do, you guys. You do not, and let me go up here to show you, all right? It says use the first and last test points to determine the end behavior of the polynomial. All right, you do not actually have to plot the first and last test point. You don't need to. Okay, the first and last test point. So you don't have to plot the -296, and you don't need to plot the 136. Those are pretty darn big numbers. It's kind of hard to plot them, aren't they? What you do need to do, though, is you need to plot the numbers that are in the middle, not the first and last, but these two right here. Let's do that. Since those numbers are also kind of big a little bit, what I'm going to do is I'm going to change the scale of my y-axis to be able to fit both of these on here. And so, because I have -30, what I'm going to do is I'm going to do it by 5s right here. The -30 is still going to be a little bit off of the graph there, but just barely. All right, if I do 5, 10, 15, 20 up here, all right, that would put the 10 number, this number right here, that would put that right there, that point right on the y-axis, as it should be, because it's the y-intercept. All right, right there. And then where is this 1, -30? X equal to 1, y equal to -30. And let me count it down. -15, -20, -25, and -30 is right here if you count down by 5s. Remember, the entire axis has to be the same scale once you figure out what the scale is going to be. Okay, you can't change it down here compared to what's up here. The x-axis could be different than the y-axis, but the scale has to be the same. Each mark has to be the same distance apart, going from one end of the axis to the other. So counting by 5s down here, I get to -30. So 1, -30 would be right there. All right, now, once you have all of your intercepts on the graph, you've plotted them all, and you also have the 2 interior points, not including the first and the last, but the other ones in the middle. Once you have all of those points on here, here's what I want you to do. You need to connect the graph from the point that is the smallest x value all the way over to the point that's the furthest x value. In other words, the point that's furthest over to the left all the way over to the point that's furthest to the right. Okay, the graph needs to move from left to right, so we have to start at the point on the left and go to the point on the right, and you can't skip over any on your way. So that means that you have to start out of the point on the left, and then you have to connect, and it's okay to there's different ways that people will do this as long as it's smooth and continuous, a smooth continuous connection. So you can go something like this right here. Okay, and the reason why I went up and then down like that is because I know that as I go from this point to the next point, as I'm moving from left to right, eventually the next point's down here, right? So you want to kind of go whoop like that. Not that it's always going to go straight in the same direction. We'll talk about that later, but you can do that, all right? As long as it's smooth and continuous, you can be kind of creative with it, all right? But you have to go from the point that's furthest on the left to the next point that's the next furthest point to the left, and then the next point furthest to the left is this one, all right? until you get to what? Until you get to the point that's furthest on the right. Okay, so as you go from left to right, you can't skip any of them. All right. And so the next point, as we go from left to right, is this right here. This is the next point that's furthest to the left after this one. And then, again, it's got to be smooth and continuous. So you got to be real careful as you go to the next point right here, you guys. Do not go like this. Do not write it like that. That is not a smooth turn right there. It's got to be a smooth turn. So what I need you to do is be really careful. And I need you to go like this right there. See how I made that smooth right there? But another thing that you can't do either is you can't backtrack like this. You can't, see how I kind of backtracked like that where I went back to the left? Once you're going from left to right, you guys, you got to keep going to the right. You can make it kind of go vertical like that. That's okay. It's not theoretically supposed to do that, but I'm not going to be that picky. But don't ever go backwards like that. If you do that, it will no longer be a function anymore because that would violate the vertical line test that we talked about earlier in chapter 2, where the graph would actually hit a vertical line would actually hit the graph more than once. So if you backtrack like that as you're going from left to right, and then let's say you backtrack to the left again, you're going to violate the vertical line test when you do that. Do not do that. Make sure the graph doesn't fail the vertical line test. So you got to keep going from left to right, okay, and don't backtrack to the left. So it's kind of a challenge there, but you can do it. Just do it carefully. Make sure it's smooth still. All right, and then we go to the final point right there. Now, we're not done yet with the graph, but that's what you need to do first. Connect the point that's furthest to the left to the point that's furthest to the right in a smooth, continuous manner where the graph continues to move from left to right, okay, not skipping over any of these points along the way. So the leftmost point to the next leftmost point to the next leftmost point, all the way until you get to the rightmost point. Make that a smooth, continuous connection as this says you have to. Now, there's one last thing we got to do. This is where the first and last point comes into play. All right. The way a polynomial function works is that when you look at the first point and the last point, there is going to be an arrow that darts out from both of those points here. The question is does the arrow go up or does the arrow go down? And yes, it could turn back around, you guys. Sometimes it does that. So don't think that just because it's going in that direction that it can't turn back around. It could. But these numbers here tell you whether or not it does that. Here's the thing. If the function value is negative, that means that the graph is going to go down like this. And the reason why I know it's going to go down that way as opposed to going, say, this way over here is because if it went this way, that would violate the vertical line test. And the other reason why I know it's going to go this way is because negative 296... all right, which is way, way, way down here somewhere because it's such a big negative number, but it pairs up with negative 6, which is right there, isn't it? So as long as you point down towards negative 6 for x and negative 296 for y, as long as you point in that direction, that's all that matters. You don't actually have to go all the way down to negative 296 and find that point. As long as it points towards that first point that we got right here, negative 6 comma negative 296, that's fine. But that proves that because the y is negative, all right, we're not going to turn back around and go up there. All right, so when the y value is negative, we point it down. When the y value is positive, as it is over here in this point here, you're supposed to take the last point right here, you guys, and you're supposed to either go up with an arrow or down. But this y value being positive 136 instead of negative 136, that proves that since 3 comma 136 is way, way, way up here somewhere, okay, if it was negative 136, it'd be way down here, right? But because it's positive 136 on the y value, it's way up here, all you got to do is just point in that direction. You don't have to do anything else. Okay, so let's review here. You plot all of your intercepts and your interior points, not the first and last yet. You do the connection like we talked about a minute ago from the first point on the left to the last point on the right. Then you do your first and last points right there. You use those to figure out where the arrows are going. And you connect the arrows from the first point and from the last point. All right. And it creates this smooth, continuous graph. If you move from left to right, a smooth, continuous graph that has what? It has arrows on the ends. Okay. All polynomial functions have to have arrows on the ends when you graph them. All right. And so that is how you do a polynomial function when you graph it. Let's try that again down here. This one's going to be a little bit easier to do. All right, number 2, because of the fact that it has, it's already been factored basically for you with all those brackets there. So let's take a look at that. So again, here in number 2, we have the brackets here, but we still go through the normal process here. We need to find the y-intercepts and the the y-intercept and also the x-intercepts. When we find the x-intercepts, which is always the most challenging part of the whole problem, all right, not as necessarily as much here though, because the factoring's already been done for us. But we set the function equal to 0 to find the x-intercepts. All right, the good news this time is that we have what here? We have, and I can expand it. When you have a bracket taken to a power, when you do the factoring part where you got to set each factor equal to 0 and all that stuff to find the zeros, all right, to find the x-intercepts, if you've got a bracket taken to a power, go ahead and expand that out. It just makes it look like a problem that we're used to. It looks like a problem from the last section, all right? And you can see here that when you have a bunch of brackets being multiplied and then also a term in front of that, those are all your factors right there, as long as there's nothing else other than the brackets and the term in front, okay? So that proves right there that there's 5 factors there. So we set those 5 factors equal to 0. All right, as long as it, but anytime that something is in that form right there, where you just got a bunch of brackets being multiplied with maybe or maybe not a term in front, that's already in factored form and it's already been completely factored as long as the brackets are all prime. And they are all prime because whenever you got 2 terms and x to the first power, okay, which we've seen so many times, 2 terms and x to the first power, that's prime. All right, you don't need to factor that down anymore, and those are linear factors anyway. So like we said, if you've got nothing but linear and quadratic factors, all right, that's the other reason why we know that we can move on here. When you break it down to linear and quadratic factors, you can, even if it's not prime on the brackets there, you could still set these equal to 0. All right. Yeah, this is not one of those problems where you got to set each bracket equal to 0 if they're the same. All right, just do all the different ones. We just want to know what all the different numbers are for the x-intercept. So it's not that like the end of the last section where you had to say x minus 3 times right here. You don't need to do that. Just tell me what all the different answers are. When you have x squared equal to 0, as we learned in the last section, that means that the only way that can happen is if x is 0. These other 2 are going to be x equal to 3 and x equal to -1 when I get x by itself. All right. So once again, we have 3 x-intercepts. What's the y-intercept going to be? Well, it's a little bit tougher, although not too much this time, because it's not a polynomial. It's got brackets in it. So you can't just say, oh, hey, it's the term on the end, like we said in the last problem, the term that doesn't have the variable in it. Now, we got a little bit more work to do here, but let's plug in the 0 for x, as you always do when you're figuring out the y-intercept. If I do the parentheses, all right, I get -3 and 1 right here. But can you see what's going on? I'll go and write that out if you can't see it yet. No problem, all right. That's okay if you can't see that yet. But this is going to end up being equal to 0. Again, you might see that already. Because when I do the exponents after the parentheses, I get 0 times -27 times 1. But 0 times anything is 0. Okay, and so I'm going to go ahead and plot the x-intercepts. All right, -1, 0, and 3. And the y-intercept already is on there, okay? It just happens to be in exactly the same place as the second x-intercept that we got. All right, so you don't need to, if you plot it again, it's just going to be sitting right on top of what's already there. So we're done plotting the intercepts. What do we need to do now? After we plot our intercepts, we then do this number line thing again like we did in the last problem. You break it up into different parts here based on how many intercepts you have. You only put the x-intercepts on here, you guys, not the y-intercepts. Just the x-intercepts, and then breaks up into 4 parts. What are going to be these 4 answers here? Okay, if I go from negative infinity to negative 1, how about plugging in negative 2 into the original function? Okay, what is that going to give me here? It's going to give me, if I plug it into the original function, I get negative 2 squared. Let me write that down. I get negative 2 minus 3, which is negative 5. I'll just figure that out now since we got to do parentheses first anyway. I'll just do that here. Negative 5 to the third. And then when I plug in negative 2 here, I get negative 1, don't I? Okay. What is this going to be? Again, exponents come before multiplication, you guys. So we have what? We have 4 times negative 125 times negative 1. If you multiply those 3 numbers together on your calculator, you guys, you get what? You get positive 500. Positive 500. Okay. And so let's move on. Again, you don't have to plot the first and the last one, right? We talked about that. So don't worry about the fact that that's such a big number. That's not going to deter us here. The next one here, we need to plug in negative 0.5. All right. And that's going to give me a little bit tougher to plug that in because it's a decimal. But I need to plug in something in between 0 and negative 1. So negative 0 point something. Anything where it's negative 0 point something would be between 0 and negative 1. All right. And so plugging that in, I get negative 0.5 squared. Zoom in there. I'm going to get a little bit, I'm going to have to write a little bit smaller here. Negative 0.5 minus 3 is negative 3.5 to the third. And then finally, when I plug in negative 0.5 right here in this last bracket, I get positive 0.5. Okay, I need to move over this interval here just so I could fit that in there. So let me do that. There we go. And doing your exponents first and then doing the multiplication, we end up getting 0.25. I don't know if I can fit this in here, but negative 42.875. All right. You don't have to write all this down here. Just get me the answer here, like I said in the last problem here. All right. You can just figure out what it is. Just be careful to do one step at a time, though. If you're going to do, say, on a piece of scratch paper or something, what does this end up being equal to? Here's the thing. There's an exact answer. Your calculator can give you an exact answer here. All right. But since whenever we're graphing a point, you guys, in that case, normally you can't round off unless you're told to. But when you're graphing, because decimals, it's hard to graph them exactly where they are anyway. I'm okay when it's a decimal to round off to, like, say, the nearest tenth. And so that's exactly what this ends up becoming. If you round it off to the nearest tenth, it is negative 5.4. Okay, so, and that just means that it's between negative 5 and negative 6. All right, so again, you don't need to be any more precise than that. All right. If I plug in a number between 0 and 3, say we plug in 1. If you plug in 2, that's fine as well. It won't give you the same answer, but you'll still have the same basic shape of the graph as somebody else would have if they had plugged in a 2 or plugged in a 1 instead. And so that's what's important. All right. So if you plug in a number that's different than somebody else did, it doesn't. Your points might be in a slightly different place than their points are, but the graph, the shape of the graph rather, is still going to be basically the same. All right, it's going to, all the key parts of it, all right, are going to be basically the same. It's going to have that same basic shape, and that's what's most important. Exponents here are equal to 1 times negative 8 times 2. All right, and that's going to be negative 16. And then finally here, if we do f of 4, we're going to get 4 squared, which is 16. We get 1 to the 3rd power. 4 minus 3 is 1. And then we get 5 over here. So 16 times 1 times 5 is going to be 80. Again, you don't have to graph 80 because it's the last, first and last numbers you don't have to graph. All right. So let me plot the two middle points again, though, like we did in the last problem. You just don't have to plot the first and the last, but you got to plot the other numbers on your number line. Where is negative 0.5 comma negative 5.4? Negative 0.5 comma negative 5.4. That's what they're asking us to graph here in the second point. All right, that is going to be negative 0.5 is somewhere around here. Negative 5.4. Now let's see here. We have negative 5.4, negative 16. Should I change the scale of the y-axis? I should, because negative 16 needs to be able to fit on here. So what I'm going to do is I'm going to do this by threes. Okay, I'll go 3, 6, 9, for example. So that means that down here, you guys, it's the same. Negative 3, negative 6, negative 9, on down, and eventually you get to negative 15, and then negative 18 would be right here. Here's negative 15. Negative 15, there we go. Let me do that a little bit better. There we go. So negative 15, negative 18. All right, and so plotting these points here, negative 0.5 and negative 5.4. Remember, negative 5.4 is between negative 3 and negative 6. It's going to be about right here, that point right there. Okay, and then negative, pardon me, 1 comma negative 16. 1 is right here for x. Negative 16 is right here. Okay, so we got an interesting thing going on here, don't we? All right, it kind of just goes scattered around here, like. But remember what I told you. All right, you have to start out at the point on the furthest on the left, and then you've got to hit every point as you move from left to right. You can't skip this point and go to that one, for example. You go to the point that's furthest on the left, then to the point that's next furthest on the left. In other words, the point that is the next smallest x value. All right, so the point that's furthest on the left, then the next point that's furthest on the left. In other words, the next point that's the next one as you go from left to right, and then the next point that's furthest on the left. Just hitting every point as you go from left to right. All right, not skipping over any. And then so as you're going from left to right, all right, you can't, if you pass over, say for example here, you can't go from this point to this point. You can't pass over as you move from left to right a point that's already been plotted. All right, so how am I going to get from here to here to here to here and then to there? Well, it's kind of tough in here, right? But again, we just got to be careful about it. All right, I want to go what? I want to be smooth here. See how I'm being as smooth as I can here? All right. You know what? I need to try that again there. Okay. This is going to be, let me zoom in there. I really want you to see this. All right. You can make it kind of like a bowl shape right here where it turns smoothly here. And then it's gotta go down here eventually. So you got to go like this. in order to be able to go down here to get to this one, this has got to be a smooth turn here. All right. And so, yeah, I know it's kind of hard, all right, and I'm not going to be too picky as far as I'll give you the benefit of the doubt if it looks close to being smooth. Just, again, don't just go like this, you guys. You cannot just do sharp turns like that. I know it's hard, but I will give you the benefit of the doubt if I can see that you're at least trying to make this a smooth turn, just like turning an automobile, you guys. Yeah, automobile doesn't go like this, does it? It doesn't go in these sharp turn formation. You can't do that with a car, but a car can do this, can't it? It can do that. It's hard to do it with a car, but it can be done. All right, where it does those sharp turns like that, but not V-shaped sharp turns where it just suddenly goes this sharp like that. Where it suddenly goes from one direction to the other. Okay, you can't make it look like a V shape. It's got to be like a U shape or an upside down U shape. And that's what we're talking about here. There we go. So then when we go to the next point here, again, it's okay to get vertical here just as long as you don't go backtrack to the left, like I said in the last problem. And then that gets us to this next point. Now, the next one's a lot easier, right? You just have to go like this right here. All right, that's not too bad. Okay, but when the points are that close together like that, you might want to consider, and maybe I should have, changing the scale on the X to where you have each point is each mark is say every couple marks is one, like for example, doing one right here and then two right here, spreading it out instead of doing 1 and 2 like you normally do. Okay, every couple marks could be a 1 and then 2. You can if you want, but this is fine right here. This will work as well. All right. Just make it look smooth or at least reasonably close to that. So I did it though, you guys. I connected the point that was furthest on the left all the way over to the point that's furthest on the right. All right, not skipping over any points along the way as I move from left to right. So then it brings me to the last part here, which says what? It says that if the first point here is a positive y value, I'm not talking about the x, I'm talking about the y value. I'm sorry, that fell off. I'm still zoomed in there. I apologize. If the point there, the first point is positive, all right, on the y value, we don't care about the x value right now, just the y value, all right, then that means that this is going to point upward towards that positive y value. Remember, you're pointing upwards when you're going in the positive y direction. So we want to point towards what? -2, 500. That's what you want to point towards. All right. All right. You don't have to plot -2, 500. It's way too far away to do that. Just point towards it. All right. And then here we need to point towards what? 4, 80. But because the y value is positive, we're not going to turn back around and go in the negative direction. No, no, no. We are going to point towards 4. X equal to 4 is right here. And then 80 is way, way, way up there, isn't it? And so we're just going to point towards it with the arrow. You got to have the arrows on each end here. And then that's it, you guys. Now, notice I said you don't have to plot the first and the last, but you do need to plot, no matter how big they are, you got to plot the middle numbers here, and we did that. So that's why I had to change the scale on the y-axis to fit both the -5.4 and especially the -16. All right. If you don't plot the middle numbers, there's not going to be a connection in between your graph here as it all comes together in the middle. You got to have it come together in the middle. All right. But since the ends have arrows anyway, you don't need to go all the way up to 80, and you don't need to go all the way up to 500. All right, so we did the same thing we did in the last problem there. All right, a nice smooth continuous connection from the first point to the last one, and then you use the arrows to finish it off on each end. Okay, so that is problem number 2. All right. All right, here in the problem number 3 right here, we have once again, we need to set this in order to find the x-intercepts. We need to set this equal to 0 here. Let me give me a second here to do that. equal to 0. And now we need to find the solutions to that equation, because since we set y equal to 0, then that will give me the x-intercepts then. Well, again, you can see here, first of all, we always look for a GCF to factor out, but there isn't one. In other words, the GCF is equal to 1. So then, since this polynomial on the left-hand side is a degree that's higher than 2, it's actually degree 4, that means that we need to do synthetic division to try to factor this thing down. Okay, we need to do synthetic division. How do we go about that? Well, we don't have a 0 to try. Okay, they didn't give us a clue like we did in some of the problems in the last section. We can't do the conjugate zeros theorem like we already talked about in the first problem. Can't do that here. So we have to rely on the rational zeros theorem. The rational zeros theorem says what? It says that we need to do factors of the coefficient that is for the term that doesn't have a variable. All right, that goes on top. You don't have to say negative right there, because we're going to end up doing plus and we're going to end up doing positives and negatives anyway. Just say 2, and then the bottom is also 2, because that is the coefficient of the leading term with the largest exponent. What are the different combinations here? We have plus or minus 1 and plus or minus 2 on both the top and the bottom. But if we take all different combos of that, we get what? Let's go through that. Fortunately, the list is not nearly as big as in the first problem that we did. 1 divided by 1 and 1 divided by 2 gives me plus or minus 1 and plus or minus 1/2. All right, and then 2 divided by 1 and 2 divided by 2. 2 divided by 1 is 2. And then 2 divided by 2 is equal to 1, but that we've already got that one on the list. So we've just got 6 possibilities we got to try out here. And like I promised, you should be able to get down to linear and quadratic factors, which is all that you need to do by using just the whole numbers and the negative whole numbers potentially. You don't need to use the fractions in order to get down to that in the problems that I give you. So again, for the sake of time here, I'll tell you right now that one of the numbers that does work is positive 2. So let's plug that in, and you'll see how it breaks this thing down to smaller factors. Okay, let me put that in here. And again, I'm just doing the normal synthetic division that we've done so many times here in the last few sections. All right, and there it is right there. Okay, so what does this mean? This means that my equation, when I factor the non-zero side, it is going to be x minus 2 all right, and all those coefficients are positive. All right, so but that's what it breaks down to there, doesn't it? Using that bottom line here for that second bracket. All right, now, what now? Now I need to take the, I now have what? I now have a linear factor, but then this factor is not quadratic or linear yet, so I still need to break that thing down. Okay, we continue to look at some potential things you can use in the synthetic division or in the rational zeros theorem. Okay, continue to try out those. Remember, just because 2 worked before does not mean that it couldn't work again. It could work again. All right, and we'll find out here. Okay, it's, but as it turns out, actually it doesn't work again. But I'm just saying, in some problems, and we've seen this already before, where just because a number from the rational zero sum works once doesn't mean you can't try it again. It could work again, and you could end up with 2 factors that are the same as a result. All right, but as it turns out, it's -1. -1 is going to be the one that works for the next part here. So I'll put -1 here. Again, we're just trying to factor the remaining part that we still need to break down. The x minus 2 is already done because that's linear. We want linear and quadratic factors. So just take the factor that is neither linear nor quadratic and put that in the top of the synthetic bar and see if we get a remainder of 0. If we do, then we can break that factor down, hopefully to linear and quadratic factors. All right, so we get, let's see. And there you go. So what does this break down to here now then? Well, the x minus 2 is already there. Okay, that doesn't change. But then this bigger bracket here, as a result of this synthetic division, and as a result of the fact that the remainder is 0, all right, I can now say what? I can now say that out of this bracket right here, we get x, and then you change the sign of the outside there like always, so that's going to be x plus 1, all right, and then this right here tells me the second bracket that goes with that this breaks down to. So we got two brackets over here. Because we're factoring the second bracket here with this synthetic division, we're now going to have a total of 3 brackets. X minus 2 is still there. And then we got what? We got x plus 1, as I already wrote down, and then 2x squared plus 3x plus 1. All right. And so there you go. We set each one of those things equal to 0. All right. Now that I've got all linear and quadratic factors, that's what those are, I set all of those equal to 0. And you solve those, and that will tell you what your x-intercepts are. So I get what? I get x is equal to 2, x equal to negative 1, all right? And then this last part here is, let's see here. I got 2 times 1 is 2, but it needs to add up to 3, so that's going to be, let's see, 1 and 2 for that. But I know that at the last step of the Berry method, I can factor a 2 out of that second bracket right there, so I end up with this right here. Setting those equal to 0, I get what 2 answers, you guys? I get, let's see here, I get x equal to negative 1/2. Negative 1/2 on this one right here. And then negative 1 again. So I see 4 answers, but I actually have what? I actually have 3 x-intercepts because 2 of those answers are the same. And again, when you're doing the x-intercepts, you don't need to repeat the answer here on the number line. All right, we just want those 3 different possibilities there. I am going to go ahead. It's going to be even more important in this problem, especially with these x numbers being so close together. I am going to go ahead and do this. I'm going to do exactly what I thought about doing in the last problem, which is to spread these out here. This is going to be 1. This is going to be 2. All right, and then so on. This is going to be negative 1. All right, and then this is going to be negative 2 right there. It's going to make it a lot easier. All right, so where would these points go? All right, you might be wondering, how do I know to do that? All right, well, if you're not sure how to spread that out, or if to spread this out, with spreading these numbers, stretching them out like that, if you're not sure about that, whether or not you should do that, just wait, you guys. Just wait until you're done with your number line. Look at all the numbers you have. Look at all the x's you have and all the points that you need to plot. And then look at all the y's that you got and the y's that you got to plot. And then decide, okay? But because my x's already, it's becoming evident that they're so close together, I want to spread this out. And so that's how I know. X equal to negative 1/2 is one of my x-intercepts, so I'll put it there. X equal to negative 1 is another one. So you can see they're so close together there that we really need to spread that out, especially this time. And then the other one is way over here. That's not an issue since it's so far away. It's not so jammed close together. Okay, but there is your 3 x-intercepts. What is your y-intercept? That's always, or, well, not in the last problem necessarily, but definitely a lot easier than finding the x-intercepts. What is the y-intercept? Again, If you've got a polynomial, you guys, with no parentheses, just a bunch of monomials being added and subtracted, the answer is always going to be the term that does not have the variable in it, because the terms that do have the variable in it are just going to become zeros when you plug in 0. And so the answer here simply is -2. All right. I'm not going to plot that yet because I don't know where my y's are going to be yet. I always like to wait, especially on the y values, all right, until after the number line is done. Let's see what we get here. I've got what x-intercepts do I need to put on this number line here? I need to put -1 first, since that's the smallest one. -1/2 is the next smallest one, and then 2. And once again, it breaks it up into 4 intervals. It's not always going to be 4 intervals. It's not always going to be 3 x-intercepts. It just worked out that way this time. Okay. If I plug in f of -2, because -2 is in between -infinity and -1, okay, plug it into the original function up here. Plug it into this original function. All right, I won't show all the work right here. We all know how to plug a number into a polynomial now. You just need to be patient with your calculator and figure that out, okay, when it's like a homework problem or a test problem or something like that. All right, but it ends up being equal to 12. If you plug in between -1 and -1/2. Now remember, if you put -1/2 in your calculator, you know that that's -0.5. So what's between -1 and -0.5? Well, how about -0.6 or -0.7 or -0.8? You can do any of those. I went ahead, or I'm going to go ahead and do -0.75, but you can do any of those other ones I just said right there, as long as it's between those two numbers, -1 and -1/2, which is -0.5, if you think of it in decimal form. So if I plug that in, all right, and it's pretty nasty, all right. Fortunately, we don't have to do decimals that much, but it ends up being approximately equal to positive 0.1. Positive 0.1. Remember, it's okay when you're graphing x and y to round off your x's and y's if it's a decimal. That's okay. All right, because it's not gonna. It's like I said before. It's hard to make a really perfect graph with decimals anyway. So approximating is okay. Between -1/2 and +2, anytime you have a negative and a positive, 0 is always in between that. And I'm going to choose that because I already figured out that number. So why do it again if I don't have to? Or why do a different number if I already have one that I've figured out, I mean. Okay, we've already figured out 0, so we'll use that. We found out up here that that was -2. All right. And then finally, between 2 and infinity, I'll plug in 3. You could plug in 4 or 5 if you really want to. But for 3, it's going to be, after you figure out a really big number, 112. Now remember, you don't need to worry about plotting the first and last number. We're just concerned about the two middle numbers right here. Those numbers are very small, so I don't really need to change the scale normally between the x-axis, or between, or we don't normally have to change the scale on the y, but because this number is so small this time, not big like it was when we had -16 in the last problem, for example, but when it's really, really small, I would also recommend, just like we did with the x-axis, to spread this out. Okay, how about 0.5? Same thing as 1/2. All right, 1.5. In other words, every single point there is 0.5, a distance of 0.5 to the next one. Just like the x-axis, every couple points is 1, and then 2, and then 3, and then you don't need to put 0.5 and 1.5 right there. I'll know that that's what you mean. So every couple points is going to be 1, and then 2, and then you could do a 3 up here even if you need to. All right. Okay. So where would -2 be? That would be all the way down here, because again, every couple points is -1, and then next couple points is -2, and so on. That's how we did the y scale, just like the x scale this time. Okay. I've already got the x-intercepts on there. I also definitely need to plot the two middle numbers, right? Let's see where they are. Negative 0.75 is somewhere around here, but then positive 0.1 is really, really close to the x-axis. It's definitely between 0, y equal to 0, and y equal to 0.5. So I'm going to put it right here. That's good enough, all right? And you can see here that, well, we'll talk about that in a minute here. Let me do the other one. Negative 2 pairing up with x equal to 0 is going to be right there. And so we now have all of my points for the x-intercepts, the y-intercept, and the two middle points here. That's what you always got to start out with. Plot all of those, all of the intercepts, and all of the points from the number line other than the first and the last. I have all of those on there now, so what do? I start out at the point that's furthest on the left, and then I go all the way to the point that's furthest on the right in a smooth, continuous manner. Okay, your graph doesn't have to look exactly the same as, say, somebody else that's doing it, as long as it's in a smooth, continuous manner, and you do not skip over any points. You do not backtrack and go back to the left like we talked about earlier, but you start out at the point on the left and you keep moving from left to right, keep moving to the right until you get to the point that's furthest to the right. So let me go ahead and do that here. All right, nice, smooth, continuous movement here all the way until you get to that point right there. Is this exactly what the graph definitely looks like? In other words, does the graph definitely go down here? Can I go all the way down here and then come back to the 2? All right, what if the person that I'm studying with, for example, decides to go all the way down here and then come back up? You're both correct, as long as it does that smooth, continuous manner. Okay? If you guys go on into a calculus class, they will tell you where this turns around. We're not in calculus, though, so you don't need to show that. You don't need to show exactly where it turns around. Okay, if your graph doesn't turn around exactly where a calculus class tells you that it's supposed to turn around, that's okay. All right, I'm not expecting you to know calculus. All right, this is college algebra, so you're good. All right, just have it follow that smooth, continuous pattern that I talked about. The last thing, as we did in the first couple problems, the last thing we need to do is the fact that the first point and the last point are both positive. That means that the arrow going from this point and also from this point has to go up because the y value is positive on both of these. Okay, so this one's definitely going to go up. In fact, it's going to point towards what? It's going to point towards 3, 112. So here's y equal to 3 is over here, excuse me. All right, and then it's going to point towards 112, which is way, way, way up here somewhere, right? So just, again, point towards it, like that. And then this thing has to turn around, you guys. It has to turn around and go up. All right, it's not going to keep, it looks like it wants to go down, but it's not going to do that. So, again, make this smooth here. Make it look like a U here. All right. Don't go like this. All right, don't make it like a V, make it like a U. I know it's kind of hard there because it's tight. It's a tight space right there. Okay, as long as you don't deliberately make it look like a V, I'll give you the benefit of the doubt here. If it looks like you're trying to make that smooth, all right, not being too picky here. I know it's a tight space there. All right, and then have it go what? Have it point towards negative 212. We don't have to graph it again, this point. We just have to point towards it since it's the first point there. So negative 212 is going to be somewhere up around here. And so just point towards it, all right, and you're good. All right, and that is the full and complete graph right there. All right, doing the middle part in a smooth, continuous manner, doing your arrows on each end. Okay, making sure that all your points are on there. Okay, because the more points you have on there, the more detailed it is. So I do need you to put all the points that I asked you to put on there in order to make it as detailed as possible. All right. By the way, this last problem that you see down here, you can skip this. All right. This is actually related to something that we did already in a previous section. All right. And so I'm going to skip that here. All right. It's been covered to an extent already. not exactly the same, but it's a similar thing we did in a previous section. So just you don't worry about knowing this, okay? If you know the stuff from the previous section, which will be part of what I ask you to study because it's part of the worksheet packet, all right, then you'll be fine. All right, so this concludes section 3.4, graphing polynomial functions. All right, as usual, contact me with any questions, and I hope you enjoy your day.